Yes, thank you for letting me presenting here today at the International OPCUA Day about my topic, which is device and update management based on OPCUA Part 100 devices. Let us take a brief look at the agenda. First, I want to talk about the motivation for device and update management. After that, I will give you a very brief introduction into the PLC Next ecosystem, the PLC system from Phoenix Contact, on which we implemented the device update model in the address space of the OPCUA server. And then we take a look at the software update specification within the DI standard. After that, we take a look at our concrete realization of the device update model, followed by the update process within this realization. And then we switch from a device-centered look to our device and update management, short DAUM solution. We take a look at possible architectures for the device and update management solution. We take a look at the user interface, and we take a look at current boundaries regarding vendor independence. And then we close with summary and a brief overview of the benefits of the DAUM solution. Okay, let us start with the motivation. So when developing a new automation platform and ecosystem today, security is a fundamental market and law requirement. This includes also a method for updating devices to fulfill IEC 62443. But today, firmware and security updates are usually made available on the product website and are then rolled out and installed device per device manually. Such a manual and fragmented approach on site with multiple tools and insecure method is not only a security risk, but it's also non-functional and not efficient at all. So what we need is a central point to monitor, manage, and update our devices. And this is where DAUM comes into the game. Now let us take a brief look at the PLC Next ecosystem. The PLC Next ecosystem includes, sure, the PLC Next controller hardware, but also the extensive runtime system, the PLC Next store concept for easy provisioning, distributing, and purchasing software, and the PLC Next community. In the picture on the right side, you can see the whole system with its interfaces. And one interface is OPCUA, maybe the most important interface. OPCUA is represented in the PLC Next ecosystem as integrated client in the runtime, integrated pub/sub in the runtime, integrated server in the runtime, and various documentations, sample code, and open source tools. The structure of the address space of the server is not only vendor specific, but the OPCUA specification Part 100 devices has been adopted here, and this is what enables vendor-independent software updates. Okay, let us take a look at the OPCUA specification Part 100 devices. The DI information model is a companion standard based on the basic OPCUA information model and is maintained directly by the OPC Foundation. It is intended to form the basis for other companion standards if they aim to model devices. The DI specification describes three models which build upon each other. First, the base device model, the device communication model, and the device integration host model. And moreover, there are two add-ins defined in the DI standard. One is the locking model, which is a generic add-in to control concurrent access on a device, and the other is the software update model, an add-in to manage software in a device. As I said, the DI standard is the basis for other companion specifications which aim to model devices. For example, some are OPCUA for PLC Open, OPCUA for Profinet, and OPCUA for IO-links, which build upon the DI standard. So subordinate systems, according to these standards, can implement the software update model. Let's take a look at the software update model specification itself. The software update model, as I said, is defined to manage the software of a device. This can include the installation of new software, the updating of existing software, and updating firmware, and also a limited backup and restore functionality. Important is that the specific steps for performing the actual realization are implementation specific for the device. Only the information model as an interface is defined in the DI standard. Okay, let us take a look at our concrete realization of the device update model. A snapshot from the OPCUA server address space is shown on the left. As you can see, the software update model consists of 4 nodes. The first is loading, which contains methods for writing files, update files to the device with cached loading option. I will explain later what this means. The second is the prepare for update node, which contains methods for stopping the device and preparing itself for update. The third is the installation node for the installation of previously loaded files. And the fourth is the confirmation node, where you can set a confirmation timeout. And if this set, the device waits for a confirmation. If it receives no, it makes the update undone. As I said, we use cached loading option. This means that loading software to the device and installing the software are completely separated. 2 more things I have to say about our software update model. The first is that we use standard OPCUA file transfer. A file can therefore be generated and opened through generate method. The method then returns a file handle, and the file handle is then used to write content to the file, and the close and commit method deletes the file handle. The other thing I have to say are that we have here 3 versions. The pending version is the software which was just written to the device. The current version is the software just running on the device. And the fallback version is the software to fall back when a update process or one installation process fails. Okay, let us take a look at the installation process itself. We call first the prepare for update methods. Then the device stops and prepares itself for update. Then we can install the software package. When the software package is installed and there is no confirmation timeout set, the update is complete and the device can be resumed. If there was a confirmation timeout set and the confirmation was received in time, the update is complete and the device can resume. If there was no confirmation received, the device switches back to the fallback version. The update process therefore failed, and the device can then be resumed with the fallback version. Okay, as I said, we switch now from a device-centered perspective to our concrete device and update management solution. Our concrete device and update management solution contains of 4 steps and 1 circle. The first step is to take inventory. Here we inventory hardware, we record status and parameterization of devices, add new devices, and remove old devices. The second step is to identify tasks. To define update patch cycles, current security vulnerabilities, new software features, parameter changes, identifying device problems, and so on. The third step is evaluate and plan. We perform risk analysis, determine update priority, and plan the rollout. And the fourth step is provision. Here we install the software updates, report on progress and errors, and evaluate and optimize the rollout process. Let's take a look at the integrated global discovery server, which is an integral component of our device and update management. The GDS is the central server to find OPCUA servers in the network. It also handles certificate creation, distribution, and management. It has an integrated PKI and also an interface for an external PKI. And the GDS also supports reverse connect. But if you don't want to use the integrated GDS, you can also connect to external GDS servers. So now let us take a look at architectures for the device and update management. And the first architecture I want to show you is I would call it common architecture. Here we have a factory network containing our devices we want to monitor and update. We have an IT network where the device update management is running on a Windows machine or on a virtual machine. And optionally, we have a connected external network where the device and update management can pull firmware from external firmware repositories, for example. But the other architecture, which is also possible, is this one, where we have device and update management running on edge. It's then operated through a local PC or laptop over its web UI. Yeah, that is also possible. Okay, now let us take a look at the user interface of our device and update management. This is how it looks like. On the start page, on the overview tab, you get an overview of the scheduled update plans, available updates, expiring certificates, outdated trust stores, and archived update plans here in this execution log. On the OPCUA servers and clients tab, you can connect OPCUA servers and clients, register servers to the GDS, approve reverse connected servers to be used, and approve servers that were announced by a local discovery server to be used. On the Assets tab, you get an overview of all available assets in the system. Assets are devices that can then be updated. And now it is important. This can be the device on which the OPCUA server is running, but also subordinate devices that are accessible via the OPCUA server, for example, IO-Link devices. On the Update Plans page, you get an overview of all update plans in the system. You can configure or delete existing plans, create new plans, add assets to the plan, and so on. Here is important that on this tab, you only see update plans that have not been executed yet. Executed update plans you see in the execution log I showed you before. And the last tab we talk about is the Update Packages tab. On this page, you get an overview of the update packages. Currently, there are two types of update packages: firmware and software, which means PLC engineering projects. Software, PLC engineering projects have to be imported manually to the device and update management. Firmware can be pulled from the vendor Phoenix Contact specific Q repository, which leads us to the next point: current boundaries regarding vendor independence. Also, the Q repository is Phoenix Contact specific. It is already possible today to integrate firmware from other manufacturers and thus make it available to the DAOM. For this, the firmware must be in a specially formatted package and there must be a QJSON file. And today, this must be generated manually for third-party firmware. But in the context of the DI working group of the OPC Foundation, there are currently efforts to standardize a package format. And parallel to this, current research and development in the context of Manufacturing X and Factory X is working on distributing firmware packages via the asset administration shell in a vendor-neutral manner. Okay, now we are near to the end of my presentation. So let's summarize what we heard now until now. With our DAOM, one can schedule and execute secure firmware updates for OPCUA-based devices. We can connect to the Phoenix Contact Central software repository, to the CUA repository. We can secure roll out and update PLC engineering projects. We have support for local discovery servers. We have an integrated global discovery server. We can use also external PKI. We can manage OPCUA server certificates and browse OPCUA values. The solution is offered as app for edge devices and also as Windows software, and we have a full REST API available. And what are the benefits of device and update management on one point? We decrease security risks due to outdated firmware. Firmware and patches from manufacturers are provided automatically. We have fewer compatibility problems thanks to specifically released software versions. We reduce support effort and decrease downtime. And how I find maybe the most important point is simply that the DAO makes it easy to inventory hardware and firmware data on one central point. And what could be possible extensions for the future? Well, one extension could be, as I said, that we move away from the vendor-specific queue repository to a vendor-independent one. And the other possible extension for the future could be to use vendor-independent formats for update packages when it's then specified. Okay, now I'm at the end of my presentation. Thank you for your attention, and I hope you enjoy the rest of the day. Thank you.